Okay, so we're going to get started with the second part of the LHC, and it's going to continue on a little bit of a turbo mode because we've got the time pressing on us on getting out of here for the colloquium. I will talk on two subjects. The new Higgs results from CMS. You have seen the combined and the Atlas alone from Mainland the first day, and we're going to see some of the updated channels with the almost 5 inverse femtobarn from CMS. And then I'm going to change a little bit gears, and I'm going to go into the SUSY a little bit on the searches for SUSY searches, or what we call even searches for dark matter candidates. And I will insist a little bit on something that you people might have as homework at your institutions, namely what are the spherical cows when we're doing calculations for direct, indirect, and LHC searches for dark matter and what we mean. Okay, so you have seen this main point to take home from this slide is that for the Higgs production at 7 TeV collisions, the dominant production is the gluon-gluon fusion, which is here. This is the cross-section, this is Higgs plus X, and this is on a log scale. This is the mass of the Higgs. We're going up to 1 TeV. Now, you probably know that there is a calculation for unitarizing the WW longitudinal scattering amplitudes between 1.2 TeV and 1.6 TeV, that things can go wrong if we don't have a Higgs-like electroweak symmetry breaking mechanism, okay? So that we're plotting these things only up to 1,000, and one can actually start thinking whether it makes sense to talk about Higgs after 300 or 400 GeV, or whether this is something different. Okay, from last year, the challenge that we had, the experimental challenge that we had, both for Atlas and CMS, was to use all the channels and have a projection for what would happen with 5 inverse femtobarn at 7 TeV. We did this when the machine was projecting that we would have 1 inverse femtobarn, but in fact they gave us 5 inverse femtobarn, okay? So what we see here is the 95% confidence limit on this ratio of the cross-section over the cross-section of the standard model. So all these plots that have sigma over sigma standard model assume standard model couplings and the standard model Higgs. So they are, if you want, model dependent. They don't apply for fermiophobic Higgs and for other kind of Higgses, all right? So what we see basically, and this is the significance of the observation. This is the numbers of sigma in some way that sigma makes a sense. The easiest way for you to think of sigma is the number of signal events over square root of background. We can do a lot of statistical tricks, etc., but this is the rule of thumb. So what these projections were saying is that if the standard model Higgs boson would be in the low mass range, and low mass range we call this range, we could start seeing excesses with a significance of 2 to 3 sigma. This is those. And the channels here would be Higgs to gamma gamma, Higgs to tau tau, Higgs to BB bar. These would be the channels. Higgs to WW star. We don't say it out loud, but we will see it in the plots, that the biggest sensitivity, even more than the Higgs to gamma gamma, is the Higgs to WW, when we're going to see it from the results. In any case, every channel does contribute to the sensitivity, and this, again, is expected. So when we say expected, is by doing the hypothesis testing, assuming a standard model Higgs hypothesis from our estimation of what the standard model signal looks like, and the observation is the data. So the CMS had updated 8 of the channels with almost 5 inverse femtobarn, and this is the branching ratios of the Higgs to the different modes. And so in the plots that we're going to be seeing of limits, we're going to be seeing features when the WW enters, when the ZZ enters. So these branching ratios bear on the cross-section that we measure, times efficiency times acceptance, okay? So when you see in the ZZ something peaking in the at 200, at 180 GV, this is that kinematically the channel is open, it's 2 times 80, okay? And so this is what, this plot, we would see features from that in the translation of the limits. So these are all these new channels. I'm not gonna show you all of them. In the previous slide, I had the page with all the public CMS results, which had been updated for the seminar 2 weeks ago, and you can see everything there. But we're going to start here with what we left last time, which was the CMS diphoton mass spectrum, where we have a discrepancy. So for this, we looked at the final plot here, the M gamma gamma. We said that what we don't see by eye, we do statistical analysis in order to figure it out. And we discussed very in detail what are the detector experimental requirements in order to understand and improve this type of search, which is a high resolution, low mass, QCD background search, okay? Now, other than the plot that I showed you before, these are the plots of the invariant mass spectrum for the different, we said last time, we have good types of photons and intermediate types of photons, and that has to do with an interaction with the material, whether they are converted, unconverted, whether they're in the barrel region, in the central region, or whether they are in the, what we call the end caps. And the reason is because the resolution, the transparency change, all of that is changing as a function of eta. So what I'm showing here is all the 4 different categories. And the Higgs here is with 5 times the standard model. This is a Monte Carlo. This is the Monte Carlo blip of how you would expect to see it in those 4 categories. Main observation, here the resolution is different than here. So the barrel ones are the ones with the best resolution. And the reason for that is what we discussed yesterday, the previous time on the detector. We had, this is the result, where you remember from Elam what was the interpretation of the green bands and the yellow bands, as well as the expected, median expected, plus minus 1 sigma, these are the yellow and the green bands, and the observation. Now, the observation is this wiggly line, and every time that the observation is out of the yellow, it means that we have a discrepancy, and that discrepancy can be a deficit or can be an excess. So every time that we have dips here and the peaks, we will see them accordingly in the limit plot. But the most significant of all these is here at the 124 GeV, where we had this, where we have this excess. So the compatibility with the background here, with the background expectation, is off. Now, we have done extensive studies of the background fit model, and I remind you this is QCD, the background is QCD, and you can fit it in many ways on the sidebands, whether you fit it with an exponential or a polynomial. You have to be careful on how you do the correlation, the error, the correlated errors, how you do the calculations. But for us, what we did a 5th order polynomial. Atlas did an exponential, and we find in the same region approximately the same kind of excess, which is what makes it very appealing.
When we say 5th order polynomial versus exponential?
Yes.
5th order polynomial versus 5 parameters?
Yes.
Exponential 1 or 2?
3 with a normalization. With a normalization.
The exponent in the exponential is what order?
Is 1st order.
So what?
Well, actually, 2 parameters, yes. It's 2 parameters. We have done it with 3 parameters where there is a second order in the exponent. So we have tried also higher order terms in the exponent, and we have tried also higher order polynomials, let's say. Now, when you do these higher order polynomials, you may think that you are fitting everything with your wiggles, etc., but you don't. Okay, you just make sure that that there is no bias in the final result. If we did it with we did do it with an exponential, and not much changed. Okay, so it's only for the correlated errors that we used that, and one could do something which said that maybe we should put a triangular and an exponential and so on, and then change our cuts and see if a resonance would persist. And these tests are also done. And one is doing the test also of doing all the pseudo experiments with 5th order polynomial or with an exponential, and see what is the percentage of time that you get the data. So all of these tests have been done, both for Atlas and CMS. I think Atlas in the next iteration, they're going to also move to a polynomial. But we're going to see how this is going to look, because this is going to be very interesting on whether all this, when we see the next time that we see this type of plots, is going to be with 10 or 15 inverse femtobarn next year, and it's going to be an extremely interesting time. This is basically how this lecture is going to end. Now I will move to the point that I was just telling you, that we must not forget that the WW sensitivity in the low mass region is very high. It's actually higher than the photons. The photons are here, and the WW is just here. So it's taking over at around 117, 118. The closest you are to the line, the more sensitive you are, and therefore, when we start combining the channels, if whatever we see in one channel is a standard model Higgs, we have to actually see what's going on in the other channel, because you may be excluding on the WW what you are seeing on the gamma gamma. And that could be the case if this is not the standard model Higgs. All right? And at this particular moment, with the results you have seen already, and with what we are discussing now, we cannot exactly say, we're just, this is the cliffhanger of the season ending for this Higgs, okay? The expected, with 4.6 inverse femtobarn, the expectation, yes? The previous. The wiggles, you mean? Right, so there is a deficit, but when you do your fit, in the cases that you have the dip in the background, the fit is putting a negative signal there in order to fit. Okay, so this is an effect of the. It's not that you're excluding the standard model background, which one could think if you have 1 3 sigma up there and 1 3 sigma down there, does it mean that you have excluded here the standard model background and you have found something else here? No, this is an artifact of the fitting procedure. And this is why this kind of plots, it's good in the end when we are going to have the discovery or the limits. We are going to be looking at the physics plots more than the wiggly plots of this type of limit plots that bring a lot of questions about the methodology. But pretty soon things are going to be very clear, and we're not going to have this kind of discussion. But thank you for pointing this out. All right, so now here is the point. And this is where you're sitting over 1 GeV and you're pondering the expected exclusion or the expected sensitivity for the WW starts at 125. So the WW right now, if it excludes 125 and the gamma gamma ceases at 124 or at 126 in Atlas, it starts making a lot of questioning. Elam showed you a plot of this wiggly structure, which is the limit, overlaid between Atlas and CMS. And there is 2 GeV difference in where the dips and the peaks are. So now the question is, in the month that comes ahead, do we understand our energy scale calibration, or is this the same thing, give 1 GeV up for the CMS and 1 GeV down for Atlas, and this is the same thing? And we're talking about 1 or 2% in the absolute energy scale that one could be offset, okay? So I will go quickly on the analysis of the WW. It's a beautiful analysis, and it's more than one analysis. It's many analyses. We have cut-based boost decision trees with training on Monte Carlo and shape analysis, and we are preparing a new analysis with applying some razor variable in order to actually get a better resolution in the WW case. When you have neutrinos and you try to make masses, you know that you're not making actually masses, and your resolution is, you're making transverse quantities, transverse masses, and your resolution is actually not optimal, okay? So there it is, WW, 2 leptons, 2 neutrinos. This is one of the candidate events. The missing ET is from the neutrinos. You've got the lepton, electron, and muon here. This is the delta phi between the 2 leptons. And now here plays role for all the angular correlations, whether you've got a scalar, a pseudoscalar, and so on and so forth. So you've got handles with the angles. So here are the signal characteristics, and that we are taking into account in order to design the analysis. And here is the design of the analysis. And the challenge is to control all these backgrounds, W plus jets, the Z plus jets, top, single top, WW, and we're going to see also how the cuts are sliding as a function of the different Higgs masses. I'm not going to go through this table, it's too detailed, but I'm going to show you here. This is cut by cut with the Z veto, jet veto, B tag. You're doing cut by cut all the different cuts in order to reduce the backgrounds we mentioned before. So we start with a Drell-Yan dominated background. This is the Z plus jets. And this, you have missing ET cuts and Z veto, and then the next steps is a top dominated sample. You do the B veto, you reject the top with the B veto, and then you are reaching down here, 3 orders of magnitude, you've got the WWs. And now you do kinematic cuts that depend on the Higgs mass and also on the characteristics of the scalar nature of the Higgs. So here is a background, a TT bar background candidate. We cannot see it very well, but we see that there is a muon, there is missing ET, an electron, and a jet, and this is rejected once you do the B tag veto. In other words, you say, I don't want to have large impact parameter, I don't want to have a B quark, and therefore this event gets away. So it was in the 3rd to 4th order of magnitude reduction of the background. Here the analysis is split into the 0 jet bin, the 1 jet bin, and the 2 jet bin. And we're showing here what is the observations in the data and all the background predictions for the 0, 1, and 2 jet bin. And in general, we see that there is an agreement. This is a Higgs to WW candidate. I think I had it yesterday also in the plots, but it is large missing energy, an electron, and a muon, and the delta phi is 35.4, and the mass of this thing is 140 GeV. Now, in the 2-jet category, this is what we call the vector boson fusion selection, where you have 2 jets in the high eta regions. The photon VBF I don't have because it's not approved. I know you wanted to see it, but Guido has not. And so I can't show it to you. What I am going to say that if you put it in the final result, the result does not change. You just have one more channel that is shown in the 5. We have 5 channels where we have the excess, let's say, in a broad region between 115 and 124, 125. If we add that, the excess doesn't go away. It doesn't get much enhanced, but it doesn't go away. This is the VBF selection for the 2-jet category for WW, and what we see is that we have agreement between the data and the predictions, and so the way the VBF only results are used in order to put this 95% confidence limit is shown here, and the limit, it's excluded 150 to 185, so it is competitive with the other channels, and this is the 150 to the 185. And one can do a fermiophobic Higgs type of model that has higher cross-section, and you exclude here between 150 and 190 a little more, okay? Now, if we combine all the channels, the 0, the 1, and the 2 jets, for the 4.6 inverse femtobarn, this is the expected and the observed exclusion. The expected is 128, 236, and the observed is tighter on the lower end, so 132, and about what you expected in the high end, 238. All right? Now, every time you see that the red curve is above the observed, whether it's Bayesian or CLS, the median expected, it doesn't matter, it agrees. But for the entire region that red is above the dashed, it means that there is an excess. And so what we see here, the 1 sigma band is here, and the 2 sigma band is the yellow. So what we see here is that starting from the low mass all the way to 160, I would say, we have a 1 sigma excess over the entire region. And now, other than doing just cut and count, you can start using invariant masses and combinations of invariant masses and try to do shape analysis. And this is a boosted decision tree output when you are using a number of shapes. The shapes are the shapes of the variables that we used to cut, but now we are fitting and we're making use of the shapes themselves. So you expect that you are going to gain something. And indeed, the results of the shape analysis, which is performed in 110 to 600 GeV, show a little better sensitivity. It is at 120 GeV, it's 1.6 times the cross-section, the standard model cross-section, and this is the limit. Again, what we see here is that this is the observed and expected plus or minus sigma, the green and yellow bands, and what we see is that here we have we're a little closer to the median, and in some cases we are at the 1 sigma down here. So the expected exclusion is 127, 270, and the observed is 129 to 270. So when we cannot exclude in the observed exclusion what we expected by a few GeV, it means that we have some excess. And now we go to the golden channel, the 4-lepton. This is a beautiful channel to do the Higgs search in a wide range of masses, and it's very clean. The 4 muons was the one that I discussed last time on how the experiments were built the way they were built, and we are able indeed to have a fantastic, I would say, resolution in this analysis. This of the analysis that I'm going to be talking so far, the Higgs to gamma gamma is the very high resolution. The Higgs to WW is lower resolution. Higgs to ZZ very high resolution, and we will see the results in the end according to that. So the baseline selection is rather simple. You've got the Z, the first and the second Z to be in a window, and you've got the mass of the 4 leptons to be 100 over 100 GeV, and what we expect is 67 events, and what we observe is 72. You don't see very well here the data, they are binned according to the resolution, so it's high resolution, but you will notice that it is low statistics still. This is why when we were talking about the ZZ and how we build the detectors, we said that we did the physics TDRs with 100 inverse femtobarn and 1,000 inverse femtobarn in order to take advantage of these golden channels. At any rate, we break these to 4 electrons, 4 muons, and 2 electrons, 2 muons. And you see the background compared to the observations. Okay? And so if we are going to plot them with the uncertainties on an event-by-event basis, these are the central values of the masses on an event-by-event mass resolution and uncertainties for the different categories. You see that we've got those 3 events at 119, and this is those 2 plus this 1 when we do it on an event-by-event. This is why this is a little separate plot, and it might be a little difficult to read, but these are in the 4 muon, you've got these 5 events, of which 3 are sitting at 119, and then we've got the 4 electrons observed, 3 expected 1.7, and the 2 electrons, 2 muons over here. So all in all, we observe 13 when we expect 9.5 plus minus 1.3. And I will remind you here that there is 1% resolution for the muon PT, and 1%, it translates to 1 to 2% resolution in the invariant masses there. So this is a very... The things in the circles is the 3 of the 5 4 muon events. These are the 4 muon, they are red. And they are at 119 when you do them event by event. So when ALAM was... The other ones is electrons, and the blue ones are the 2 electrons, 2 muons. Okay? And we have to take it this, I mean, this is the statistics you have. It's 13 events. All right?
The fact that the electrons and muons are behaving differently?
No, not at all. I expect that. I know that. The muons are the highest resolution we have. The electrons have a little bit of a higher energy scale issue, and this is why we're going to be comparing with Atlas. So if there is an offset there, if we're talking about a phenomenon that it is showing itself in the photon and in the ZZ, and it's the same phenomenon, we have to reconcile the 119 with the 124 with the 126, and there are issues there which have to do with the calibration, the absolute energy scale, and the resolutions the way we understand them, and we're going to figure that out. For the electrons, for the electrons it does. For the electrons it does, because you have all the, yes. But we have to, again, we have to keep in mind that these are 13 events, and if it's there with 10 or 15 inverse femtobarn this time next year, earlier in the summer of next year, we will know. Okay, so I told you to remember to register before what is happening when the channel opens, so we cannot exclude here because the cross-section is, the branching ratio is changing and it's becoming very high. However, this excess that we were talking about is this little thingy here, this little edge here that is going over the 2 sigma on the yellow band. And this is at the 119 GeV. The wiggles here, the more wiggles we see, the more it means that this is a high resolution analysis, all right? Okay. So the other low mass of the analysis that I had on the first table is the Higgs to tau tau. And I'm showing this only because it is very important that we understand and reconstruct taus all the way from the first year of the LHC. It's a very beautiful analysis, and if we look at the final limits, you also see this is the expected on the red, and this is the observed as the function of the Higgs mass always. This is a law, it probes the low mass region. You see we even started 110 where LEP had excluded. You see that we do have this smooth excess in the entire region also in this channel, which is curious. Okay, so if we take, now we will see all this spaghetti type of plots with a lot of graphs, and I will try to make it very simple. Here we are seeing the sigma over sigma standard model, and here we're seeing the 95% confidence limit again on the sigma over standard model in the for the same integrated luminosity, and what we are looking is 100 to 600, the entire region, and 110 to 160, the low mass region, and where the channels of the low mass region play a role. So this is what we saw in the beginning for the expected, but now these are the observed. And we still see that indeed, where we expect the WW to take over because of the 1 sigma, it's almost the same as the gamma gamma, but we should not underestimate the sensitivity of the gamma gamma, of the WW. If we want to look at the different yellow and green bands again, for the standard model Higgs hypothesis, the 95%, the preliminary exclusions with the are for the observed is 125 through 600, when the expected was 117 to 543 at 95% confidence level. And at 99% confidence level, not much changes except on the high mass region. On the low mass region, the observed is 128, when the expected was 125, and the upper one is 525 with 500. So this is the, again, here the 100 to 600, and here blowing it up from 110 to 160, 90, 95, and 99%. The CLS is giving you the percent, the CLS should be the 0.05 actual value of this CLS index of the test statistics is telling you that this is a 95% confidence level, or if it is 0.01, it will be a 99% confidence level, and so on. And the simpler plot to look at, which is also Elam showed you, for now everything combined, also of channels that I didn't show you, is that we, the 95% exclusion, the observed 95% exclusion is 127 to 600, when the expected was 117 to 543. So 117 to 127 we don't exclude, although we would expect to, and the reason is because of these 5 different channels having these excesses. Let's zoom in the low mass region. This is the 3 channels together, the BB, tau tau, WW, and this is the 4 leptons and gamma gamma. Remember what I told you, these are the high resolution channels and these are the lower resolution channels. And we are seeing again the same plots with the plus or minus 1 sigma expected over the median. Here we see that up to 130 we have the over 1 sigma excess on all the low resolution channels, and here we see for the high resolution channels here we see the 119 and the 124, one dominated by the photons, one dominated by the 4 leptons. So the way we, in our talks, the way we say that is that we cannot exclude the presence of the Higgs, of the standard model Higgs, below 127 because of the excess of events in the region between 115 and 127.
theoretically immodest.
Yes, that is correct. That is correct, and this is where everybody here, a little bit in the history of particle physics on how we do statistics, is that we are now entering to the Bayesian church of how we think as a the prior expectation, let's say, of the knowledge that we build of 30 years. The fact that these blips appear where you expected them for 30 years, or whether there is a favorite region, it gives it a weight that statistically in our modeling we can only take into account if we use Bayesian inference. If we are agnostic about any theory and whatever, and we just play roulette, then but we're not playing roulette here, this is physics. And depending on who you ask, they will tell you, one party will tell you, well, we had even 4 sigma and it went away, or 3 sigma and it went away, and another party will tell you, well, I published the top quark evidence paper with 2.8 sigma. Why? Because I was expecting it was there.
No, but the point I wanted to make was, namely, this modest excess of events, if you were to attribute it to, for example, the standard model Higgs, is immodestly produced.
Give me, I have 30 minutes, so you will see the pools. Yes, you will see the pools. It's immodestly produced, it's more than we expect, but within a sigma, it's not so immodestly produced. It's more by a sigma than what you would expect of the one standard model Higgs. That is correct? Yes? Yes. Yes, so it is. No, it's 1 sigma, yes, theoretically modest you can call it, yes. Yeah, but all of this will be settled very, very soon. I will skip the p-values, you have seen them before, and I will show you this. This is David, and everybody of course, but since you were asking, this is the pools for all the channels that we mentioned. There were the 5 channels that are showing the broad, modest, immodest behaviors. The pools for an assumption of 119.5 GeV Higgs and 124 GeV Higgs. And there you have it. There are 5 measurements that are statistically very little correlation, except for how you calculate backgrounds, so you have to be careful. But there you are. Okay? So all individual channels are compatible with the best fit excess in the low mass region, whether you attribute it to this or to this. Okay? So I find this plot a very nice plot to show for how we've got these 5 channels. And then, of course, the challenge is, and the good thing about having 2 detectors is bringing it together with Atlas and figuring it out. Now, what has happened is that the new electroweak plots, where we started from yesterday, they have transformed. There is this little sliver here of allowed region. There is this little sliver here of a standard model Higgs mass that would be in the low mass range. And you see here the 114 on the outside, the 300 in the middle, and the 1000 on the outside of the green. And this is the ellipsis, and that's because they are correlated, of LEP2 and Tevatron, and all the polarization data and LEP. Okay, here it's only CMS. So this is how our knowledge has changed in December 2011. These plots have been prepared for taking into account the new data. And already by doing that, I should say that what I told you yesterday, that we're going to be doing precision measurements at the LHC is already sort of happening.
Question. In the 70s, the fact that the tau and the charm were very near in mass caused a lot of confusion
Yes.
for about a year or 2. Now, would it make, if you had a 2 Higgs hypothesis, would it change in any way your analysis, or you don't care if these are particles or what?
No, we will figure it out because we have a program where we're going to be able to measure the spin and the CP and figure out if this is 1 or 2 particles. This is not a difficult thing to do. We will do it very easily. So what I wanted to say here is that let's assume, I'm not going to go through this, but I'm going to assume now that we have a discovery of an approximately 120 GeV resonance. The immediate question is therefore, other than is it 1 or 2 or 3, all right, which makes a difference, but all right, we can do it. Is it spin 0? Is it CP even? To what extent can you exclude a CP odd component? Does it come from a weak doublet? Are its couplings proportional to masses? Is it a composite or an elementary? All of these questions we have to answer. Are there other neutral or charged resonances? Does other things decay into it? And have we looked at all the possibility associated production of this thing? So now, to change gears for the final 20 minutes, the good news is that the current Higgs region allowed is SUSY friendly. And I will talk a little bit about SUSY now. There is a very large number of SUSY signature explored at Atlas and CMS. They are all based on large missing energy in the phase space, large MHT or HT, the scalar sum of all the jets, and a large combination of different kind of leptons. Right, so we've got dileptons, trileptons, single leptons, plus jet, plus met. This is the type of, and then we go into the reconstruction and we have Z plus met, tau plus electron plus jets plus met. But this is where we are moving in terms of the phase space for SUSY signatures. The interpretations are presented both by theorists and experimentalists in many frameworks. And since this school is about trends, the trendy thing to do is to have an interpretation in the PMSSM, which has the 19 parameters, instead in the M-SUGRA with the 5 parameters, instead in a reduced parameter space. But I want you to remember that when we do M-SUGRA, etc., we are checking final states and our sensitivity of our analysis with these different signatures. We're not per se, we don't care per se to exclude M-SUGRA because it is already, one might say, excluded from the flavor physics, all right? So then the other trendy part is what we call SMSs, or the simplified models. These started from the offsets. Maybe you can ask Nima when he's here to tell you a little bit about that. But the simplified models is basically cutting it short with the decay chains, keeping some of the particles and calculating particular final states without having all the mass spectrum, so sort of segregating part of the mass spectrum that you don't care about and only keeping the final particles, and so you can have a separate signature for stop production and not involve the rest of the MSSM or the full SUSY parameter space, or a separate one for just dijets and neutralinos, and so on. These are very trendy. And they are infinite, so it doesn't matter how many you make and you can cook up more, okay? The reason why they're useful is for a quick look at how we probe the space and for a quick understanding of how the analysis works in different theoretical scenarios. So if you make your own favorite theoretical scenario with these SMSs, you can take the analysis from the experiment and translate them in your model. So the analysis methods are targeting both discovery and characterization, and they are merged now in a clever way. It used to be that we took from the Tevatron the classical analysis with excesses in the tail of missing energy, and we had in the meantime the transverse masses along the lines of the transverse mass of the W, which the transverse mass is bounded by the mass of the parent particle, and you can extend what we learned in the standard model from even the neutrino edge all the way to the mass of the W, the transverse mass of the W. You can extend this in signatures with 2 weakly interacting particles with 2 LSPs, not only 1, and try to make clever kinematic variables, okay? Now, I will make a few comments in the next 5 transparencies about dark matter, and model building, right? So the thing that you do when you solve the gauge hierarchy problem, which is a problem that you are faced, that we are faced with in particle physics. The first thing you have to do is you cook your model such that it respects the electroweak precision and all the other measurements of the standard model. In order to do that, usually you have to insert a new discrete symmetry. And Michael Dine told you about R parity, which is that symmetry in SUSY in order to respect, for example, the proton decay. It can be the T parity for little Higgs or some other conserved, some other discrete symmetry. And when you do that, this stabilizes some state in that framework, so somebody becomes stable. And again, it's either in the little Higgs models or in UED models and extra dimensions models. Somebody becomes stable. In this case, though somebody who becomes stable can be, depending on its interactions, attributed as a part of the dark matter, is a good dark matter candidate. However, you have to, you learned something about cosmology in this school, and you have to be careful. When you calculate the relic density of a given candidate, you calculate it, you don't measure it. And that requires the mass and the interactions. And these are relevant to how it annihilates in the early universe. And all these words here mean that you assume some thermal histories for the early universe, and that the universe cooled down, and what you have right now in terms of dark matter is what you started from, minus those that annihilated. And in most of the theories, in fact, what you get is you get non-thermal relics, for example, from gravitino decays, and extra entropy. It decays to other stuff, it decays to photons. So the people who are doing G2 compactifications, models and strings, etc., they find non-thermal histories, they find non-thermal relics. That doesn't mean that doesn't say much, but it's an indication that you have to be careful about all that. And it's an indication also that how we put together the direct measurements and the LHC is a tricky thing. And I will come back to this question. So I want to quickly review what happened between 2002 with the final set of the run 1 data of the Tevatron, 100 inverse picobarn, and that was an exclusion of the gluino of 300 GeV, and a factor of 25 in luminosity of the Tevatron, the 2.5 inverse femtobarn, run 2, not even finished the analysis with the entire data set because you don't increase your sensitivity at all. It means you have to build a different machine. It means you have to build a higher energy machine. More data doesn't do you good. So a factor of 25 in luminosity, it gave you only 100 GeV in gluino mass from the Tevatron. This is what we inherited, 400 GeV. 400 GeV with their 10 inverse femtobarn of data, it doesn't matter, they analyzed only up to 2.7. When we were preparing for the LHC of the 14 TeV, we were having a 5 sigma reach, that was a discovery, with 1 inverse femtobarn that would cover this space here in the M0, M1/2. I'm assuming you know M0, M1/2, so I'm not saying anything about that. And we were reaching, therefore, with 1 inverse femtobarn of 14 TeV data, a gluino of 1.3, okay, TeV. And we have not excluded that with the 7 TeV, but we are down at the 800 to 1 TeV with 5 inverse femtobarn of 7 TeV. So we are better than we would have expected given our studies of the TDR. So here is a bunch of historical papers from Zwicky and Vera Rubin trying to measure the rotation curves. You heard something in Eric's lectures about all that, and you will hear probably more. This is the coma cluster in X, and this is the bullet cluster, etc. Based on these astrophysical and cosmological observation, we have some sort of a conclusion that there is something going on in our universe in terms of the composition, in terms of 23% of the composition of the universe, or 84% of the non-relativistic matter. And it has to do with what we have called the dark matter, because it doesn't have electromagnetic interactions. And we have deduced that it's nearly collisionless, and it gravitationally clamps. Also, we have deduced that it's much weaker than the weak cross-section for direct detection. And what it is not, this dark matter, based on, again, adding it all up for what it could be, is that it's not gas, it's not dim stars, mostly, it's not mostly planets or neutrons, and probably it's not mostly black holes. So, yes?
Please, could you extend what do you mean by this is not gas?
It's not intergalactic medium gas type of, if you take all the density of that, it would make up something that would give you the dark matter. In all of these, at least up to here, it says it's not non-baryonic.
But gas cannot stay to pure gas, I could say.
That you know better than me. Yes?
How do we know, for example, that it's not neutrinos?
We have calculated for hot dark matter, relativistic dark matter, namely neutrinos, how much it can be, and it can be part of it, but it cannot be all of it. It cannot account for all of it, where all of it comes from the W map, all of it, the summation of the W map, all of it. Nevertheless, there's a lot of interpretation there going on, okay? So one should be very careful. I think we are going to hear a lot more on the colloquium. In particle physics, after considering all the caveats of the spherical chaos, in other words, the local dark matter particles are running with 230 kilometers per second. They come from somewhere close, their density is some number that we put together, etc. These are all literally spherical chaos, assuming this, and that. If we take into account these conjectures and these assumptions, a coincidence or serendipity, if you want, is happening on any dark matter particle, any electroweak, electroweakly coupled particle of 100 GeV that is stable, would give you the dark matter you wanted just by doing this thermally average cross-section calculation for these weakly interacting particles to annihilate to ordinary particles. And this relic density is coming to what the W map is telling you. So this number here, the 0.1 of the omega chi, which is the WIMP, which can be from SUSY or anything else, as long as it's weakly interacting enough, is giving you, according to this relation, this magical number 0.1 if it is 100 GeV, which is the electroweak scale. But this is what we have taken to call the WIMP miracle, if you want, and to take it as an evidence for support of the dark matter being a supersymmetric neutralino candidate. However, I have to say that when supersymmetry, all the good things that you learned about supersymmetry, for all the cancellation of divergences and so on and so forth, at the time that supersymmetry was being developed, this dark matter candidate was not anywhere to be advocated as a good thing for supersymmetry. It came out of supersymmetry, all right? So on the other hand, you've got all these other types of particles from axions, axenos, gravitons, in all sorts of other theories that could be potentially the dark matter candidate. So in the last 5 minutes, the one thing that I wanted to tell you is that in supersymmetry, this neutralino is decomposed into bino, wino, and higgsino So it's a combination of all these gauge eigenstates that makes this particle. And depending on its composition, the way we interpret our data in the LHC is important for whether we exclude it or not. So what I'm going to show you is the final result of the analysis both from Atlas and CMS here on where we exclude. And I want to point out this is M0 and M1/2. In some of the theoretical plots you see this reversed. And the important part here on both of these plots, this is CMS and Atlas with the different kinds of signatures. We are touching the 1 TeV, gluino, and squark over here. Same thing for Atlas, very close. That is not to say that we have excluded 1 TeV gluino. It is the maximum gluino mass that we can exclude, that we exclude is 1 TeV for the different kinds of scenario. So if we want to say the important thing about how we hold hands with the people who are doing the direct dark matter detection, is that over here is the co-annihilation, and over here is the focus points. Here it's mixed, the mixed kind of neutralino that I just showed you that has a lot of wino and higgsino component. And here is the other favored by the WMAP area, and we are excluding part of that, so we need to soon be starting talking with the direct detection people. And so I will leave it here and say that the game for SUSY at the LHC is only now starting, and that there is a lot of space and interpretations we have not done, a lot of signatures we have not looked, and that with one inverse femtobarn, the result that I showed you today, we have gone 500 GeV over what the Tevatron has done with 20 inverse femtobarn. So I'm going to leave it here and take questions. Yes.
So you showed us some inclusion plots, and you told us about the supersymmetry. You didn't show so many plots of these, and you said even from the M sugra, which I think all of us believe is already included so far, and then also of course the more interesting is the scenarios where only some of the supersymmetric particles are kept. And, but I think I heard, maybe hopefully I misunderstood it, that you said that you're always taking into account missing energy. Is that?
We try, yes, we do, except for the dilepton searches. We are trying, and the reason is the trigger. But the dilepton and the leptonic searches where you have a lepton, you don't need to have the missing ET so high. So for all the missing ET searches, what we're designing now for the next year is to go lower in missing ET and go higher in the number of combined states in the final state, so that we are not actually missing ET. We're not looking in 100 signatures in the same part of the phase space. So for these analyses, however, for the most part, the hadronic analyses, which are the most sensitive, are quite overlapping. That's why we don't actually combine them, because they are very correlated. Some of them are going in the high M0. They have a better probe. This is not to be shown actually, because it's my extrapolations, and we will be touching these focus regions, which are depending on the top mass. But those analyses that have leptons, we're designing them to go lower and lower in missing energy. Indeed.
So maybe what I'm coming at is, how many of these SUSY searches do not rely on our parity?
We have our pilot, of course, that's a good question. We have our parity violating type of searches with 6 jets, that we have correlations of the different jets in order to have our parity violating gluino production, etc. And these, I can show you if you want results from these. They are quite interesting. They take over from the Tevatron, but we have a gap between 160 and 200, 144 and 200 GeV where we have not covered, and the Tevatron hadn't covered either. These are the 6 jet analyses. We do have our parity violating, of course, of course.
Are there any more questions? Maybe one quick.
There is one more?
Yeah.
No, I think we want to thank Maria and Delan Gross for finally bringing experiments to our schools. We waited for that a long time, and you worked so hard, so thank you. Okay, now we are doing an Eliezer tour to the Raka Institute, back to the